Welcome to The Explainer. Today, we're talking about an unseen thief, a little gremlin that lives inside pretty much every piece of tech you own, silently stealing energy.
Okay, let's start with something you've definitely noticed. You unplug your phone, you unplug your laptop, and you touch that little power brick, right? And it's warm. Sometimes it's actually pretty hot. So what's going on there? Where's all that heat coming from?
Well, that heat you're feeling, that is quite literally wasted energy. It's the symptom of a huge problem, something engineers are constantly fighting against. It's called magnetics loss, and it's happening deep inside the tiny magnetic components, the transformers and inductors that are the heart of all your gadgets' power systems.
All right, so a little bit of heat. What's the big deal, right? Well, it turns out it's a massive deal. In fact, this loss is one of the single biggest roadblocks we have to making our tech even better, even faster, and most importantly, smaller. You see, it's not just about wasting a little electricity from your wall outlet. The real problem is that all that lost energy has to go somewhere, and it turns into heat. And heat, well, heat is the arch nemesis of electronics. It can fry sensitive components, for sure. But here's the kicker. It's the main thing that limits how small we can make stuff. Think about it. The only reason your phone charger isn't the size of a sugar cube is because if it were, it would get so hot it would literally melt. So managing this heat, managing this loss is everything.
So, to really get a grip on this, we need to look at the two main culprits inside a magnetic component. First up, the wires themselves, just simple copper wires, the kind everything is wound with.
You know, on a basic level, this is just good old-fashioned electrical resistance. It's why a wire gets warm when you pass current through it. And if you're using simple DC, direct current, the math is super easy. But our modern gadgets don't run on simple DC. They use high-frequency alternating current, or AC. And that's where things start to get, well, really weird.
Just look at this contrast here. On the left, with DC, the current is flowing nice and evenly, using the entire wire. It's happy. But on the right, with high-frequency AC, whoa, the current is almost allergic to the center of the wire. It's all bunched up right on the outer surface, on the skin.
This bizarre behavior is called the skin effect. What's happening is the high-frequency magnetic fields inside the wire are creating these tiny swirling currents. They're called eddy currents, and these little whirlpools basically push back against the main flow in the middle of the wire. So what's the result? You've paid for this nice thick copper wire, but the electricity is only using a tiny fraction of it, which means its effective resistance goes way, way up.
Okay, so your inner engineer is probably thinking, simple, if the resistance is too high, just use a thicker wire, right? I mean, more copper equals less resistance. That's basic electronics.
Yeah, you'd think so. But in the strange, counterintuitive world of high-frequency magnetics, that is completely wrong. It's just like this professor said. You're sitting there, you think your loss is too high, so you put in a fatter wire, and you watch in absolute horror as the resistance and the heat actually go up. How is that even possible? Well, the culprit is an even bigger, badder version of the skin effect. It's called the proximity effect. See, in a real component, the wires aren't just floating in space. They're wound tightly together, layer after layer. And the magnetic field from one wire starts inducing those wasteful eddy currents in the wire right next to it. And that wire does it to its neighbor, and so on and so on. It creates this destructive chain reaction of wasted energy. And the scale of this problem is just staggering. We're talking about the AC resistance jumping up to 30 times higher than the simple DC resistance you'd measure with a multimeter. Think about that. Your careful design, which on paper should have been 99% efficient, suddenly turns into a glorified and very tiny space heater. But believe it or not, the wires are only half the story. All those copper windings are wrapped around something, a central magnetic core. And guess what? That core has its own totally different set of problems.
Okay, so in a perfect world, a magnetic core would be like a perfect spring. It stores energy and releases it with zero loss. But a riddle core, it's a little sluggish. There's a lag. The magnetic fields can't quite keep up with the electrical force being applied to it. And this lag creates what engineers call a hysteresis loop. And that area inside the loop on the graph, that represents pure, unadulterated energy loss, turned into heat, every single time the current switches direction.
And this type of energy drain is called hysteresis loss. What's actually happening is you're spending energy to physically force all the tiny magnetic particles inside the core to flip their direction, back and forth, millions of times a second. It's basically like microscopic friction. And just like regular friction, it generates a whole lot of heat.
And just when you thought it couldn't get worse, it does. Many core materials, like ferrite or steel, are also conductors of electricity. So that means, you guessed it, those same pesky eddy currents we saw in the wires can form inside the core itself, swirling around and generating even more waste heat.
Okay, so let's recap. We've got wires basically sabotaging each other with parasitic currents, and we've got cores that are generating heat just by flipping their magnetic bits around. It sounds like a losing battle. So how in the world do engineers fight back against all these invisible forces?
While for the wire problem, the solution is just brilliant. It's called Litz wire. Instead of one single fat wire, engineers use a bundle of hundreds, sometimes thousands, of super thin strands. Each tiny strand is coated with an enamel insulation. And here's the genius part. They're all woven together in this really specific pattern. This forces every single strand to take turns being on the inside and the outside of the bundle. The current has no choice but to share the load evenly, which totally defeats both the skin and proximity effects. It's an incredibly clever solution. And for the core, they use a surprisingly similar trick. The problem is big eddy currents, right? So they break them up. Instead of a solid block of metal, they build the core from a stack of really thin, insulated sheets, kind of like a deck of cards. These are called laminations. Now, those big, wasteful eddy currents simply can't form. They get trapped in tiny, harmless little loops within each sheet. It's a simple idea that just slashes the core losses.
So, what's the big takeaway here? The next time you pick up your tiny, powerful phone charger and notice that it's barely warm, remember this. The magic isn't just in the fancy computer chip. It's in the brilliant, clever engineering that went into conquering these invisible thieves of energy. Mastering these losses is the real secret to making our tech smaller, faster, and way more efficient.
And that kind of leaves us with one last big question. We figured out how to tame these invisible forces, these eddy currents and hysteresis losses, to get to where we are now. But as we keep demanding more and more power from smaller and smaller devices, what other invisible forces are still out there, lurking in the physics, just waiting for the next generation of engineers to find a clever solution and unlock a whole new wave of technology?